Uh, hey, how's it going? We're live. Where was I talking? Alright, this is the note we were working. How's it going? Today we're, starting to wrap up our conversations about series. Last time I did 1,000,000 examples. This time I was hoping to go over a bunch of problems you guys did, but I got very few submissions from you guys. But I'll go over the ones I got, which are all from Joe. Hey Joe, thanks for submitting some stuff. The first one is from earlier in the homework when we were talking about sequences, before we were talking about series converging. I guess I'm not clear what the problem was. Oh, we were evaluating a limit? This is number 72. Determine if the sequence converges, and if it converges, take the limit. So what do we got? Our sequence is tangent inverse natural log n. I guess one of us is missing a parenthesis here, but that doesn't matter. The limit of this is the limit as n goes to, I assume, this is supposed to be a plus infinity? Of f of x equals tangent inverse x? Okay, so this line doesn't really make sense. The idea you're trying to do is say that you're going to replace the sequence with the function. These two equal signs don't really convey that idea. And it's not an idea that you really need to explain away. I think the next stuff gets better though. We have that the limit at infinity of natural log x is infinity. Then the limit as x goes to infinity of tangent inverse infinity is pi over 2. I think the use of the word then here is not so hot. Then makes me think you're saying this, therefore this. The tangent inverse limit isn't because of the natural log limit. I see how they're connected in the problem, but this fact doesn't follow from the fact before it, so I wouldn't use the word then here. I would maybe put and. Thus the given series converges to pi over 2 because f of x has a limit of pi over 2. The thing you're trying to get at is a really hard thing to get at. You want to say that natural log goes to infinity and tangent inverse at infinity is pi over 2. In many ways you would be able, like if you had natural log of tangent inverse, yeah, let me phrase that. So let me point out the thing you're not allowed to do in this problem. Since the limit of tangent inverse at infinity. So I guess first it's worth saying, hey, you got the right answer. Since tangent inverse at infinity is pi over 2, this limit equals the limit as n goes to infinity of natural log of pi over 2 equals natural log of pi over 2. Like, because tangent inverse goes to pi over 2, you're allowed to plug pi over 2 into here. Natural log is a continuous function, so the limit will equal the value. So you get natural log of pi over 2, and you can do this. You're allowed to do this because pi over 2 is a number, and the idea of plugging in a number makes sense. If you try to do that with the wrong order that this problem's in, tangent inverse natural log, you want to say since the natural log of the limit of natural log is infinity, then this will be the limit of tangent inverse of infinity, which is pi over 2. But you're not really allowed to say the limit of the thing evaluated at infinity. Like, you can't just plug in infinity the way that you can a number. You have to be more delicate using limits, and that's the thing that makes this problem awkward. You're getting the right number, and you're phrasing it mostly correctly. I think a good turn of phrase to have in your pocket to be able to handle these things is state these two limits. These are the two important limits. Since ln of n goes to infinity, or since tangent inverse goes to infinity, I guess you can use the symbol here. As x goes to infinity, and since natural log of n goes to infinity, we have tangent inverse natural log n goes to infinity. Here's a way of phrasing this that connects those two dots. You've got the right reasons, and you're getting the right conclusion from connecting them together. But this sentence, this given... a bigger problem. The given series converges to pi over 2. Nobody has ever talked about a series in this problem. This is a sequence. A series is when you're adding the terms. A series is a list of terms. We're just asking what does the sequence go to here. You want to be very careful that you're getting those words right. The given sequence converges to pi over 2 because f of x has a limit at pi over 2. If you want to use the limit of f of x, have you ever stated what f of x is? If you're going to use the name f, you need to define f at some point. So at some point above this, you would want to say let f of x be tangent inverse natural log x. Am I missing that? I don't think that ever got stated at some point. When you introduce a term, you need to say what the term is, unless there's some context that makes it obvious. Limit as n goes to infinity. Yeah, this phrasing of limit as n goes to x does not make sense. The thing you would want to say, I think a better way of phrasing this first line is that the limit as n goes to infinity of an is the limit as x goes to infinity of tangent inverse natural log x. Let f of x, if you really need the name f of x, equal that. I don't think you're going to get so much value shortening this expression to the name f of x that you need to give it a name. Adding more names is sort of adding more mental overhead onto the reader. Yeah, I think I've commented enough on this. Right answer, right reasons. Slightly awkward sentencing. The thing you get better at with practice. What was I doing? Oh, I have my email. Did I close? Oh, it's this thread. Okay. Next up, let's do. Okay, we got the series e to the 1 over n cubed. You're correctly getting the correct thing that e to the 1 over n goes to 1. So this is basically 1 over n cubed. And 1 over n cubed is a convergent series, or the sum of 1 over n cubed converges. It's a p-series. So this thing should converge also, maybe by limit comparison, maybe by direct comparison if you can figure out an inequality about e to the 1 over n. Let's try this out. Since e to the 1 over n and n cubed are both positive, check. And limit an over bn equals the limit of this equals the limit of e to the 1 over n equals e to the 0 is 1. I guess there's an issue that this isn't a sentence, right? I'm assuming this is supposed to be the word and. If that is something else, maybe this is a sentence, but I don't see a verb here. Since this and this, period, isn't good. I would probably, if you can put it all into one sentence, then the since construction is fine. But if you're ending the sentence, I would say we have this and that, period. And since this sum is a convergent p-series, 3 is greater than 1. The given series is convergent as well by limit comparison. Cool, this is all great. One point, you're using the phrase the given series, and then also saying what the series is, which there's nothing wrong with that. For me, I'm using the phrase given series to avoid having to write this out when I use it. Since you're already saying what the series is, the word given is unnecessary, but you don't have to delete every unnecessary word. I don't know. I've had English teachers who say just delete the unnecessary words. You want extra words if they add clarity. I guess this is adding clarity. Like, this is the series I was trying to say converges. And look, it converges as well by limit comparison. This is all good. The only main issue I would say is you've used the letters AN and BN without defining them. You're using them because the way we stated limit comparison had those terms in them, and there are definitely contexts in math where the statement of the theorem that I'm citing uses the names f of x and g of x, so I would want to say we're going to use this theorem where this thing is f of x and this thing is g of x, and I pull out those letters, or maybe I talk about the f of x and the g of x from the theorem without saying what functions they are in this context. I don't think limit comparison is a theorem that's so complicated, or that this paragraph is so complicated that you need to do that. If you're going to use AN and BN, you should say what they are, but that's unnecessary. You can delete this chunk of the equation and just start with this and you're fine. Anyone who looks at limit comparison will understand what you're doing. Yeah, this is solid. Good work. And then we got one more to talk about. And then I'm going to start talking about the next thing. And this is the wrong window. New. Cool, so you're going to do the root test. We'll let AN be this. Hey, good job giving a name to the thing. Then rho equals the limit of this equals this equals 1/2. Because rho is less than 1, we conclude by the root test that the series converges absolutely. This is all perfect. Yeah, there's no places where I want a little more detail. There's a little awkwardness that I would point out. Then rho equals this. There's two kinds of equations that you present in math. You can say, let f of x be x squared. Or you might say, therefore, f of x equals x squared. Or you might find yourself asking, when does? I guess there's three types. F of x equal x squared. There's like three different flavors of this equation has a different tint to it depending on what's going on. When I present an equation, I want the audience to know if this is a conclusion that I'm drawing, and if it's not a conclusion that I'm drawing, if I'm saying when is this true, or if I'm defining something to be true, I'd really like the explanation of that fact to happen before the sentence. It's a very common problem when you're reading math to say, if the sentence ends with an equation, and then you say after it, when will that be true? Reading math is slow and it takes a long time, and it's a thing that you're best at doing with a pencil in your hand to fill in the gaps that the author's not providing. And a very common problem that happens in reading math is this equation. How did they figure that out? Is that coming from this line? No, is that coming from this line a couple pages before? I'm scanning through the previous pages looking for what is the piece of information that I'm missing that makes them know that this is true. And eventually I'll say, well, maybe I'll give up and whatever. And I get to the next sentence and it says, oh, well, that wasn't true. They're going to figure out when that's true now. When you make an equation, you want the context. Which type of thing? Is this a thing you're saying is true? Is this a thing you're defining it to be true? Is this a thing you're asking to be true? You're pulling out the letter rho here, and it's sort of unclear which of the two versions of this is. You want to say let rho be less than 1, so you want to give it the name. And it's a little bit awkward that when I get to this point, it's not stated that you're defining that this is a definition of rho. But on the other hand, it's not quite a definition of rho, because it's the root test that is the thing that, like, rho needs to be this for the root test. I feel like if you mention the word root test somewhere before this sentence, then all of a sudden I've got the context to know where the letter rho is coming from. I guess I'm reading about series, so probably got this concept of the rho in my head already. But it's better for you to introduce that context. So, like, a thing you might think about, like, I'm criticizing because I'm trying to teach this concept, and like, if this criticism sounds harsh, it's not. This is a totally great paragraph. But the fact that you've introduced a rho, the root test is the context that makes me know what rho is. You might want to mention the root test before you start talking about rho. So I might add a sentence at the start that we use the root test. Now that I've already used the word we can say let an equal this. Then rho equals this. Because rho is less than 1, we conclude the series converges absolutely. Maybe you don't need to say the root test anymore because you already said that you're using the root test at the top. That's a little thing. I guess I should also point out, if I'm talking about English, that this is also not a sentence. We will let this is the end of the sentence. Next sentence is the start. Like, you can't just say sentence, comma, sentence. Cool. One thing I meant to say, but I didn't earlier, is I scratched out the word since here. You might also think about how this is a thing that if I'm writing a paper, I always have to go back through and manually do it because I'm really bad about this. It's not good form to use the word since twice in a row. There's enough other options that you can grab something else. Change one of them to a because. But that first one shouldn't really be a since, so you're already fixing that. Okay. That's me talking about student work on series and mathematical writing generally, and nouns and predicates. I only got stuff from one student. I generally think you don't want to walk into the exam and have that be the first time someone's reading your mathematical writing. If you don't want me to talk about it in class, you're welcome to show it to me outside. But you should probably get someone to look at some of your homework problems before you walk into the exam. And if you're okay with me doing it, I'm happy to talk about this a little bit more at the start of class for the next couple days. But we got more topics to talk about. I forgot that there's more stuff on exam 2 than just do the series converge. We want to talk about Taylor polynomials. So here's a theorem that we used before, but we didn't give a justification at the time, and now is a pretty good excuse to give that justification. Theorem. If f of x, or if p of x and q of x, well, let's give them names. If p of x is a0 plus a1x plus a2x squared plus ... up into a n x to the n is a polynomial, and q of x is b0 plus b1x plus b2x squared plus ... plus bm x to the n, m, are polynomials of degree n and m respectively. Like this is the standard form for a polynomial. The thing we said about polynomials before was when we were talking about finding it was about partial fraction decomposition, where we would clear denominators and say we're hoping this polynomial equals that polynomial. Well, the only way that's going to happen is if the coefficients equal the coefficients. And it's a statement that's so obvious that you feel like you don't need to explain it, but you do need to explain it. How would you try and prove this is the fact? If p of x and q of x are polynomials, and if p of x equals q of x for all x, then the degrees are the same. M equals n. And ai equals bi for all I. Which I is I between 0 and m, which is also n. If the polynomials are the same functions, then they must have the same coefficients. We stated this, we didn't prove it. Right now we have kind of a good excuse to prove it, which is, well, I'll do that afterwards. Why is this true? Here's how I can prove that this is true. One of the coefficients you can grab for free by plugging in 0, right? 1, p of 0 equals q of 0 equals a0. And q of 0 equals b0. If p and q are the same functions, then a0 equals b0. So we got the first ones that are equal right away. 2. So plugging in 0 lets me eliminate all these other terms and just isolate one of the coefficients. This is a way to get information about the coefficients from information about the values of the function at the points. Now I want to think about a derivative. What's p prime of x? Is the constant goes away, I get a1 plus 2a2x plus 3a3x squared plus dot 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 plus n a n x to the n minus 1. And q prime of x, if I take the derivative of this polynomial, the first coefficient goes away, I get b1 plus 2b2x plus 3b3x squared plus dot 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 plus m a bm x to the m minus 1. So, if p prime of 0 equals q prime of 0, then we get a1 equals b1. This feels like cheating, because like you might think about the definition of this number being that it is the coefficient, like the thing you get when you take the derivative and plug in 0 is a1. So like when you say that p prime of 0 equals q prime of 0, this is like about the definition of the thing you want. But remember, the definition of p prime of 0 isn't anything to do with the coefficients. P prime of 0 is defined to be, the limit as h goes to 0, of p of 0 plus h minus p of 0 divided by h. This is a way to describe the coefficient using only the values you get from plugging in the function. And the same thing for q. And so on. I guess I'm not going to try and write out a formal complete rest of the proof, but like you see the trick. You take a derivative, I guess in general, an is the nth derivative of p at 0. I guess you have to divide by an n factorial. If I took another derivative, I'm not going to get a2, I'm going to get 2a2, and I have to divide by that. The next derivative will give me 6a3. You want to divide by the a3. And bn is the nth derivative of q at 0, divided by n factorial. I don't know if you guys have seen this notation, but f triple prime is sometimes going to be abbreviated f to the 3, where you wrap the 3 in parentheses. A 3 in parentheses, a number means this many derivatives. So, because you can get the coefficients from the function values in this way, every polynomial, you can figure out what its coefficients are. If two polynomials are the same, then you know what their coefficients are. Here's the idea. Let's use this trick on a function that's not a polynomial. Let's try e to the x. Maybe e to the x turns out to actually be a polynomial. If it was a polynomial, it would be a0 plus a1x plus a2x squared plus a3x cubed plus dot dot dot. A polynomial would stop at some point. But hey, we just got really comfortable with letting you keep going forever off a point. Now that we're okay with adding up infinitely many things, maybe it's okay for e to the x to turn out to be an infinitely long polynomial. Maybe every function is an infinitely long polynomial. That's the idea of a power series. And that's what the rest of this section is about, or the rest of exam 2 is going to be about. If e to the x was a polynomial, that trick we just saw for using a function to figure out the coefficients would tell us what those coefficients have to be. a0 would have to be f of 0. That's e to the 0 is 1. a1 would be f prime of 0. The derivative of e to the x, I'm really good at doing that in my head, is e to the x, plug in 0, and I get 1. a2 would be f double prime of 0 divided by 2 factorial. The second derivative of e to the x is also e to the x. Plug in 0, you get 1. You get 1/2. a3, if it exists, would be the third derivative over 3 factorial. I know the third derivative. It's e to the x. Plug in 0, you get 1. This will be 1/6. So maybe, or conjecture. Maybe e to the x equals the sum from n equals 0 to infinity. What's our general term here? It's x to the n. Our coefficient is 1. The top of the fraction was always 1, and we divided by n factorial. This is generally going to be the pattern for these things. This is divided by 0 factorial, and 0 factorial is defined to be 1. This is 1 over 1 factorial. That's the general pattern here. Is it? Let me pull out a graphing calculator and try some junk out. Can I do this? Desmos. Desmos is a nice, pretty graphing calculator on the internet. What's our function? Our function is 1 plus x. I can't type in all infinitely many terms, but I can type in a bunch of terms and see what it looks like. X... Where's the caret? Oh, can I just write XX? No, I want a lowercase x. Hey, XX for x squared works as a way to type when I don't have my keyboard out. So plus x squared over 2. Does this... this doesn't look that much like e to the x until I actually add in e to the x. What does e to the x look like? Show me a lowercase e. Do you like the function exp? Because I don't have a... exp of x is a common alternate notation for e to the x. When I graph e to the x and I graph that function that I think was the first several terms of the infinitely long polynomial version of e to the x, I find they are really close to each other. Like, not only do they intersect at 1, not only is it tangent at 1, but it's sort of one step better than a tangent line. It's like hugging the curve in some kind of goofy way. And if I throw in another term, plus xxx over 6, oh geez, it's really hugging the curve. Like before, it was like splitting off here, but if I can barely see the difference out here on the right. If I throw in one more term, plus x to the 4th, xxxx, divided by 24, man, I can't see the difference at all over here on the right, and back here on the left, they do split off eventually. If I zoom out, I'll always find that e to the x is never going to equal any particular polynomial. But at any particular point, and in particular close to 0, 0 seems like the special place where I was defining the function, this polynomial, to be a really good approximation using the information about e to the x at 0, I get that. One thing we're doing here is kind of a natural extension of the idea of a tangent line. If I just thought about the first two terms, so maybe this is it. One thing it's worth saying, this sum to infinity, at any particular point, we're asking what this is at a particular x value. We're asking about a sequence of functions and asking, does it approach this one function? Or I can ask what's going on what's called pointwise and say for a particular x value, does the right-hand side equal the left-hand side? So far, the only type of convergence of functions we've talked about is pointwise convergence. You can ask deeper things about, does the function as a whole on the right look like the function as a whole on the left? And you can ask that in a couple different ways. We're not really getting that into this class. But it's sort of a deeper question that bothers me when I look at the graph. Even throwing in... Did I lose it? Oh, did I put it over here? Looking at the whole thing, yeah, it's pretty close at a bunch of points, but the function as a whole is not really that close to that function as a whole. You got to set that aside. For now, we're only talking about pointwise. For any particular point, at -2, it's still pretty far off, but I can believe that I saw that as I added more terms, it would hug the curve for longer and longer. I can believe that adding 3 or 4 more terms, the red function will start to get closer and closer to the blue function at any particular point, at -2, the way it did already for numbers that are not that close to 2. Okay, so that's one thing to think about. We're talking about a sequence of functions converging to a function. What that means for us, for the entirety of this class, will only mean pointwise. For each fixed x value, it will eventually get closer and closer. For different x values, it might take longer to get there. And in this case, the x values close to 0 are getting there faster than the x values farther from 0. But it kind of looks like every x value will get closer and closer as time goes by. Second thing to think about, this is a really natural extension of the tangent line. We took f of 0 plus f prime of 0, x minus 0. If you think about the point-slope form of a line, something you saw in some algebra class, y equals the y value plus the slope x minus the x value. This is what you're doing when you write out the equation of a tangent line. We have the y value is this point, we have an x value, we have the slope of the line. I've written down a line that goes through that point and has that slope. I don't know if your Cal 1 teacher talked about it this way. I think this is a really useful way of thinking about the tangent line, as it's the point-slope form of a line applied with the idea of a derivative. What we're doing is naturally extending that to get not just the tangent line, but something like a tangent parabola. I throw in a third thing, and now I've got a quadratic function that I have reason to believe is the best possible quadratic function for approximating e to the x near 0. It's going to have the correct value at 0, it's going to have the correct derivative at 0, and now it's also going to have the correct second derivative at 0. The line has a second derivative that's always 0, so throwing in a quadratic to make it even better should make us an even more useful way of approximating e to the x. You probably had problems in Cal 1 where you would approximate e to the 0.1 by using the tangent line. Well, now you can use a third term or a fourth term and get even better ways of approximating e to the stuff. So let's get to a definition. I guess a bunch of definitions. A power series is a series of the form f of x equals the sum from n equals 0 to infinity a sub n x minus some value, I'm going to usually call it x naught, to the n, where an is some sequence of real numbers. This expression is a power series centered at x naught. And it is defined whenever the series converges. You've talked about functions before. I'm allowed to just write down f of x equals natural log of x, and implied when I write that down is when x is greater than 0. Functions only exist when they are defined, so when I write down a formula, it's implicit that you're only allowed to use this formula if you're actually able to plug in a number. The same deal's going on here. F of x is this series when that series actually exists. For a series, it exists when the series converges. Which is a more complicated question than when is natural log of x defined. I can write you've had algebra questions where here's a complicated formula, tell me the domain. Well, here's a formula, tell me the domain, is now answering the question, when does that series converge? It's worth noting, up here, when we were thinking about figuring out the coefficients of e to the x, we were taking derivatives at 0. Taking the derivatives at 0 give you what you would call the raw coefficients of a polynomial written in standard form. But if I wanted to do this at a different point, I'm getting a thing that's not the coefficients. I'd be getting a thing that is the coefficients if written in this form. The key idea isn't a deep one. We're just translating a function. Like if you think about, you can always translate this function over to 0 by thinking about g of t is f of t plus x naught. Will that do it? It's a plus x naught or a minus x naught, and I never remember which, and I guess I don't care about this point. You can always translate this function to be centered at 0 instead of being centered at x naught. You don't want to have to translate the function at every time. You just sort of get used to putting in x minus whatever your value is. If I had a key thing going on is this polynomial, the statement I had was that if it's true for all x, but we only really used a small value of x's close to 0. We said what's the function at 0, what's the derivative at 0, what's the second derivative at 0. Even if they're not equal for all x, even if they're equal for a tiny interval of x values near 0, well, if I'm comfortable doing a power series at another point, I can do the exact same thing and say whatever point that the functions are equal at, which I'm usually going to call x naught, I can talk about derivatives at x naught and get the same a longer, more complicated way of getting that the coefficients must be the coefficients. So that's a power series. One of the questions we're going to ask is, I'm going to hand you a power series. I'm going to ask you, when does this converge? This is a slightly more complicated version of the type of thing you've been doing for... I've been handing you series and asking you when they converge a lot. Now I'm sort of handing you infinitely many series and asking you, when do these infinitely many series converge? And it's rough, but it's not that bad. Should I stop and do some examples of that? The idea here is we have something like an infinitely long polynomial. Yeah, okay, let's do an example. Consider the power series g of x is the sum from n equals 0 to infinity n factorial x minus 2 to the n. Here's a power series that's centered at 2 is the word I'm looking for. The problem I'm likely to give you is find when this converges. I'm actually going to give you a more detailed description that's more detailed instructions that are going to use some words we haven't defined yet. I'm going to tell you to find the radius and interval of convergence. And I'm going to be right back. I need to go take a potty break. 1 second. I'm back. Okay, I've used these words radius of interval of convergence, but I haven't said what they mean. We'll do that in a second. We could state that definition first, but I think the way you actually solve... Well, let's try this out. Pretend that it's the type of problem that we've just done, and I've handed you this series, and I'm asking you if it converges. And it's a little bit weird that the letter x is in there, but, like, what are the tools you would use to check if this series converges? The fact that there's a variable x means there's going to be some... Well, if x is like this, you'll get that result, and if x is like this, maybe you'll get that result. But, you want to be able to still use the same basic tools. Here we have an n factorial. We also have a whole big something to the n. The whole big something to the n might suggest that I try the root test. The n factorial might suggest that we do the ratio test. In general, those are going to be the best tools we have. If I think about the root test, I'm asking about the limit as n goes to infinity of the nth root of the absolute value of n factorial times x minus 2 to the n. The second part, the nth root, goes nicely. I get nth root of x minus 2 to the n, the absolute value is still there. I get absolute value x minus 2. I know what this is. I'm left with the nth root of n factorial. I don't know what that is. If you know that limit, great. That limit is rough. The nth root of n goes to 1. Does this go to 1? This is 1 times 2 times 3 times n minus 1 times n. Hey, this is a fact I should have said. Hey, fact. You're allowed to use this fact without argument. The limit as n goes to infinity of the nth root of n is 1. You've probably seen how to do that limit in a Cal 1 class. It's the L'Hopital's rule thing where you write this as e to the natural log of it. This is e to the natural log n over n. Now use L'Hopital's rule on this. This thing goes to 0. You get e to the 0 is 1. This thing shows up often enough in these classes that you kind of want that fact on the tip of your tongue, and you're allowed to use that fact without justifying it, because doing the L'Hopital's rule inside the exponent is gross. When I have the nth root of n factorial, I'm thinking about the nth root of 1 times the nth root of 2 times the nth root of 3 times dot 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 times the nth root of n. The nth root of n goes to 1, and the nth root of any constant goes to 1. All of these things go to 1, but the dot dot dots in the middle stop us from concluding that the product goes to 1. Like if there were 10 things that all converge to 1, the product definitely converges to 1. But when you have more and more things, like there's not like a version of the limit of this conclusion doesn't hold. And I don't think this is true even. So, what can we do instead? The root test doesn't work unless I'm good enough to do this limit. I don't know how to do this limit. Let's try the ratio test instead. In general, with a power series, the root test and the ratio test are the things that get the x out of the way. They are the things that handle almost all versions of the x value. The ratio test has us considering the limit as n goes to infinity. If I want the n plus 1th term, that's n plus 1 factorial, x minus 2 to the n plus 1, over n factorial, x minus 2 to the n. And in the ratio test, I'm allowed to throw an absolute value on there. N plus 1 factorial over n factorial is just n plus 1. X minus 2 to the n plus 1 over x minus 2 to the n is just x minus 2. Okay, the ratio test gave us something way simpler. This is n plus 1 is positive. So it doesn't need the absolute value. The x minus 2 is sometimes positive, sometimes negative, does need the absolute value. What is this limit? You're going to be tempted to pull the absolute value x minus 2. It's constant with respect to n, so I can pull it outside the limit and say the limit of n plus 1 is infinity. So the limit is infinity. No matter what x is, I can pull that thing out and get the limit of n plus 1 is infinity, and infinity times anything will always be infinity. But, hey, wait a minute, I just said anything times infinity is going to be infinity, and that should give you a pause for a second, because, oh, wait a minute, what if x minus 2 was 0? We get into these places where you need to be agile enough to say, wait a minute, there's two possibilities here. This limit is going to be 0 if x equals 2. If x minus 2 absolute value is 0, which is when? Which is only at x equals 2. Or this limit is infinity for anything else. This whole having an x there that I don't know what the x is going to often lead into me doing these special cases where if x is this, it's going to go this way, and if x is that, it's going to be this other thing. You got to be careful about these. You got to start thinking about what are all the special cases of my conclusions. When you divide both sides by something, double check, is that thing 0 maybe? Yeah. If you pull a constant out, you're not allowed to pull a constant of 0 outside of a limit or a derivative or an integral. Or I guess most of the time it doesn't matter because you get 0 times something. The place that it does matter is 0 times infinity does not exist. So pulling a 0 out of that thing is more dangerous than the others. The ratio test worked. What does the ratio test tell me? The ratio test, recall, if that limit rho is less than 1, it converges. Absolutely. By the way, we don't care too much about the difference between absolute convergence and conditional convergence. We will mention it once in a while. But for this x thing, we're just asking when does it converge. The interval and, yeah. If rho is less than 1, it converges absolutely. If rho is bigger than 1, including rho equals infinity, it diverges. So, 0 is less than 1, infinity is bigger than 1. We conclude that this function, g of x, is the sum of n factorial x minus 2 to the n, converges at x equals 2, diverges everywhere else. The only time it converges is at one point. I said find the interval of convergence. The interval of convergence is the interval of all points that converge. We haven't said that there's no justification for why I'm assuming that the places it converge will turn out to be an interval, but it will in a second. If I had to write that point as an interval, it would be the interval from 2 to 2, close brackets. The radius of convergence is 0. I haven't justified this yet, but we're going to see that the times that this converges are always going to be an interval that's centered at 2 with some radius. That interval might include the endpoints. It might not include the endpoints. It might include one endpoint or not the other. But it'll always be an interval centered at 2 of some radius. The radius might be infinity, in which case it converges everywhere. That radius, like you always want to answer your interval is, like the radius of convergence is what's the radius of this circle. Or calling this a circle is dumb. There's actually a circle out there in the complex plane that this is only part of. But we're not going to be talking about complex series. This is an interval of radius of 0 when you have just a point. Let's try one where the radius and the interval actually are something. Maybe this is not the best first example. Let's try when does h of x is the sum of n squared x to the n, x plus 1 to the n, converge. This one's a little more well suited for the root test. The root test is usually easier when it works, but easier in the sense of less writing. Let's try the root test. This time. The limit as n goes to infinity of the nth root of the terms n squared x plus 1 to the n. I guess there's an absolute value there also. This is the limit as n goes to infinity of, I can split this up into factors. You can do that for a root for multiplication. You can't do it for addition. Oh god, you guys are in Cal 2. If I find you doing the square root of x squared plus y squared equals x plus y, no, you can't do that. You are way too grown up to be making that mistake. What is this limit? I get the nth root of n squared times the nth root of the absolute value of x plus 1 to the n. I don't need the absolute values here because n is positive. This is the limit of, if I rearrange the order of the exponents here, I can call that the nth root of n squared. This nth root cancels. I get absolute value x plus 1. Nth root of n goes to 1. I get 1 squared. It's supposed to be a 2 out here. Absolute value x plus 1 is just absolute value x plus 1. Okay, what does the root test tell us? This is my row thingy. It converges when row is in less than 1, and it diverges when when row is bigger than 1. And when row equals 1, we don't know. We don't know anything. It's not that it's impossible to know, it's just that the root test doesn't tell us anything. The ratio test also doesn't tell us anything at row equals 1. These are things that we can solve. Let's solve when it converges. It converges when absolute value x plus 1 is less than 1. I don't know if you've solved an absolute value inequality, but if you're solving absolute value a less than b, what you're saying is the number has to be between the positive and negative versions of b. Like, you think about absolute value for a second and you conclude that. When is the absolute value of x less than a number? It's when you're between that number and the negative version of that number. So this is going to be when x plus 1 is between negative 1 and 1. That's going to be when x is between negative 2 and 0. So it converges on the interval from negative 2 to 0. It diverges, if I did the same thing to this inequality, it's going to diverge on x greater than 0 and on x less than negative 2. But I don't know what's happening at x equals negative 2, x equals 0. At those points, we don't know what's going on at all. In general, okay, so some of the questions we can answer now. You're going to be tempted to say the interval of convergence is negative 2 to 0, but the thing is I don't know if it's a bracket or a parenthesis here. I don't know if it's a bracket or a parenthesis here. We haven't thought about those. In general, for the endpoints of your interval of convergence, you need to separately work those out manually. The root test or the ratio test will give you every point on the real line if it converges, except for maybe 2 points, and you still need to know those 2 other points. Usually these are going to be very easy versions of the type of problem that you've done a whole bunch of here's a very specific series that doesn't have an x in it anymore. Does this converge or not? But that interval from negative 2 to 0, I can think about the interval. Our interval is centered at negative 1, which I knew it was going to be because this is x minus negative 1. This is a power series centered at negative 1. Our radius of convergence is 1. This is a circle centered at an interval that is centered at negative 1 with a radius of 1. The radius of convergence is 1. And I guess I should give you a heads up now that calculus books have not standardized their notation of what letters to use for the radius of convergence. Many calculus books will say the radius of convergence is called rho. And many calculus books will say that rho is the name of the limit that you get when you do the ratio test or the root test. Those two things that are each sometimes called rho are not the same. It's the worst. The radius of convergence, in my nomenclature, is usually going to be 1 over rho. Here they were both 1, is why they are the same in this particular problem. I'm going to tend to use R for radius of convergence. Actually, I'm just going to use the word radius of convergence. We don't particularly need to give it a name. We've got a radius of convergence of 1. When the problems ask about radius of convergence, this is what they're getting at. The interval of convergence is basically negative 2 to 0. It's just I don't know whether to include the endpoints. Let's figure out whether they're to include the endpoints. The series was the sum of n squared x plus 1 to the n. I want to know what's this do at x equals 0? What's it do at x equals negative 2? And we're going to see what is almost always going to happen. When I plug in x equals 0, I get the sum of n squared 0 plus 1 to the n is the sum of n squared. 1 to the n is just 1. Does this converge? No, n squared doesn't go to 0. This diverges by the divergence test. If you've gotten the hang of the last batch of problems, these are usually going to be very easy things to solve. What's happening at x equals negative 2? In general, you plug in one of the endpoints, you get a 1 to the n. You plug in the other endpoint, you get a negative 1 to the n. So in one of them, you're thinking about an alternating series, and in the other one, you're thinking about a non-alternating series. Negative 2 plus 1. I guess I should write this out. My x value is negative 2. Negative 2 plus 1 is negative 1. I have negative 1 to the n squared. Does that converge? No, this diverges. N squared goes to plus infinity. So negative 1 to the n squared. It goes to positive and negative infinity. That's an awkward phrase to say, but it's easy to say. It doesn't go to 0, which is what it has to do. This diverges by the divergence test. So our interval of convergence, I'm now able to answer with both of these answers. Negative 2 is not in the interval of convergence. The interval of convergence is the interval of points where it converges. Negative 2 is a point where it diverges, so that's not in the interval of convergence. Open parenthesis. At 0 it diverges. It doesn't converge at 0. 0 is not in the interval of convergence. Cool. In general, I'll make the statement. The way we've done the last two problems is usually how I like to do the problems, where I just use the root test and the ratio test, and then read off the answers from that. I can state the theorem. Let 1 over rho be the limit as n goes to infinity. It's not just a limit. I'm going to take what's called a lim sup. I don't know if you've used this word. I think you probably haven't in Cal 1. Of the nth root of the absolute value of an. The lim sup is defined to be the limit as n goes to infinity of the supremum over m greater than or equal to n of the value. Let's make this of a sequence Bn. So the idea, there are many sequences that don't have a limit because they go up and down forever. The lim sup is saying, hey, what's the biggest points that this sequence ever gets to? What's the highest value that it gets close to over and over and over infinitely often? If you go up as high as 1, then you go up as high as a half, and then you go up as high as a third, and then you go up as high as a fourth. Those highest points that it reaches are going to get closer and closer to 0. That would be a limit supremum of 0, a lim sup of 0. We don't particularly need to know the word lim sup. I'm stating it because this is the technically correct way of stating the sequence. Most of the problems you're looking at, the limit exists. If 1 over rho is this not use rho. Rho is the name for the thing you get from the root test. The root test talks about a limit. The stronger version of the statement works even if there isn't a limit. If you have to take a limit sup, is the strong version. Then the series sum an x to the n converges. I forgot to say centered at a point. On x minus x naught, absolute value less than 1 over rho, diverges on absolute value x minus x naught greater than 1 over rho. And when it converges absolutely inside the interval. It might only converge conditionally inside the interval. It might only converge conditionally at the endpoints. Those are the only places where conditional convergence is even a possibility. We don't usually talk about those in this type of problem. And here, 1 over infinity is 0. 1 over 0 is infinity. In this case, rho is called 1 over rho is called the radius of convergence. And the interval of convergence is the interval at which is the name for the interval of points at which it converges. The interval is negative infinity to infinity. If the radius is infinite, which is when rho is 0, it's just the point x0 itself. If the radius is 0, which is when rho is infinity, and is x0 minus 1 over rho, comma x0 plus 1 over rho, with a parenthesis or a, what's a good way of phrasing this? Is this or this or it's half open, x0 minus 1 over rho, comma x0 plus 1 over rho, let's say with a bracket and a parenthesis here, or parenthesis x0 minus 1 over rho, comma x0 plus 1 over rho, bracket, if otherwise, if rho is not 0 or infinity. Which one of these it is, you have to figure out by doing these particular tests at the endpoint. And these particular tests are usually pretty easy versions of the type of problem that we've done before. I should do another example. Let's do the one that we just conjectured for e to the x. We guessed that e to the x was the sum of x to the n over n factorial. Is it? Well, a first question is, does the sum... It's key to understand there's two questions. One, does the thing on the right-hand side even exist? Does the series converge? The second question is, if it converges, does it converge to the correct thing? And it's important to keep in mind those are separate questions. The first question we can answer pretty easily now. We'll use the ratio test. So question. What are the interval and radius of convergence? Of g of x equals the sum n equals 0 to infinity x to the n over n factorial. I've gotten way better at muting my microphone when I sneeze or cough. I'm feeling good about that. What are these interval and radius of convergence? There's a factorial. Let's try the ratio test. Heads up, in these problems are now more computational than the ones about sequences and series, so we're going to be a lot looser about writing in complete sentences and paragraphs and junk when we're doing problems like this. The limit, as n goes to infinity, of the n plus 1th term, x to the n plus 1 over n plus 1 factorial, over the nth term, x to the n over n factorial, in absolute values, is the limit as n goes to infinity of I get x to the n plus 1 over x to the n. I get n factorial on top of n plus 1 factorial. I get the limit as n goes to infinity of absolute value x times 1 over n plus 1. Last time we were in a place like this, we said, ooh, there's a special case we have to think about if the thing is 0. In this case, 1 over n plus 1 goes to 0. This is the absolute value of x times 0 is 0. I don't have to think about a special case. Sometimes x is 0, in which case it goes to 0 even more. But the two things agree. I don't have to say, well, if this, then that, and if that, the other. It's always going to be 0 here. And I don't need to... It's good to think about what if the thing was 0, but in both cases the limit is always going to be 0. So we're done. This is the place where 1 over rho, 1 over 0 is infinity. The radius of convergence is going to be infinite. I don't like thinking in terms of that. I just like thinking about what the ratio test says. The ratio test says if rho is less than 1, it converges. And we just saw that rho is less than 1 always. The interval of convergence is negative infinity to infinity. It always converges. The radius is infinity. Cool. I should do one where it's not 1, where it's finite but not a number than 1. Let's consider sum from n equals 3 to infinity. Where the thing starts doesn't really matter. X plus 2 to the n, and our coefficient is going to be 1 over n times 2 to the n. Let's not make it 2 to the n, let's make it 3 to the n. When does this converge? What's the interval of convergence? What's the radius of convergence? Here's one where the ratio test or the root test would work. The root test is usually easier when it works. I guess I should say something about the root test. When I stated this theorem that involves this goofy lim sup idea that we haven't really clearly defined, but I stated it anyway because that's the correct version of the theorem. The theorem is using the root test. The root test, it turns out, is just better than the ratio test. This is a weird, surprising thing. It turns out the root is the one that always tells you whether it converges or not. We've seen places where the root test didn't work. Why did the root test not work the times that it didn't work? Well, it didn't work because I couldn't work out what the nth root of n factorial was here. Our answer was the nth root of n factorial. We can sort of retroactively go back and say, it turns out it must have been infinity because the radius of convergence turned out to be 0. The issue wasn't that the limit didn't exist. The issue was that it was hard for us to find the limit. In general, you made a big deal about limits sometimes not existing. Lim sup is sort of the thing you pull out when you're worried about a limit not existing, because the lim sup always exists if you allow it to be infinity. There's always what's the highest value that you're getting close to over and over. If the limit exists, then it equals the lim sup. Anyway. It turns out that the root test is the good one in the theory side, but it might not always be the good one in the application side. If the ratio test works, then the root test definitely worked, it's just maybe you weren't able to work out that limit that way. If the ratio test does work, it's going to give you the same rho value as the root test. That's not an obvious fact, but if you think about where the root test and ratio test came from, they came from, if that thing is geometric, what's the r value? Those are the same thing. Okay, the root test is the one we will use here. The root test and the ratio test give you the same thing if both limits exist. You can come up with examples where the ratio test limit doesn't exist, but the root test lim sup does exist. Yeah, anyway. We're using the root test. We're thinking about the limit as n goes to infinity of the nth root of the absolute value of x plus 2 to the n over n times 3 to the n. This is the limit as n goes to infinity of, I get absolute value x plus 2, the power of n and the nth root cancel. I get 3 on bottom. The n and the n cancel. The absolute value of 3 I know is 3. I also get an nth root of n on bottom, and it's handy to know the nth root of n goes to 1. Or this is, it's not a limit anymore. I'm taking the limit. Absolute value x plus 2 over 3. So, what do I know about the root test? This thing is going to converge when absolute value of x plus 2 over 3 is less than 1, and it maybe converges when the absolute value equals 1. It definitely diverges when absolute value x plus 2 over 3 is greater than 1. In theory, I guess we have 3 different equations to solve, but you don't solve them all. Like, the solution to this is the one that you do. Then the solutions to this will be the endpoints of this solution, and this is everything outside that solution. Like, you don't have to write out 3 different things to solve. How do I solve this? I get absolute value x plus 2 less than 3. That tells me that x plus 2 is sandwiched between negative 3 and 3. If I subtract 2 from all sides, I get x is between 1 and negative 5. My interval of convergence is some interval from negative 5 to 1. I still don't know the brackets and parentheses. This is going to deal with what happens when x is negative 5 and what happens when x is 1. This tells me it diverges when x is bigger than 1, or when x is less than negative 5. You don't really talk about the end. The question they're asking is when does it converge, but it diverges outside this interval if you're outside the endpoints. The thing we have left to do is what happens at x equals 5, x equals negative 5. What happens at x equals 1? So I plug those numbers into my function, into my power series expression, and get a specific series, and think about whether I can tell whether that converges. At x equals negative 5, we get the sum of 1 over n times 3 to the n times negative 5 plus 2 to the n. Negative 5 plus 2 is negative 3 to the n. So I got negative 3 to the n over n times 3 to the n. Negative 3 over 3 is negative 1. I get the sum of negative 1 to the n over n. Usually one endpoint will give you an alternating series. The other endpoint will give you a non-alternating series. Does this thing converge? It's generally really easy for alternating series to converge. We just need to know that the thing that's not alternating is positive and goes to 0. Oh, and I need it's decreasing. And all of those are true. This is the alternating harmonic series. It converges at x equals negative 5. By the alternating series test. This is a more computational problem. I'm doing the type of thing that I do when I'm writing out those paragraphs for the other ones, but don't worry too much about getting the paragraphs right here. Like, there's other stuff going on. I'm not going to be grading you on your writing, although I will be grading you on did you use a correct reasoning. The alternating series test is correct and works. Just saying AST is enough to say it converges at x equals negative 5. It does have to be true the alternating series test works. I guess it does need to be true that it converges at x equals negative 5. At x equals negative 1, what's going on? At x equals negative 1, I'm thinking about the sum of 1 over n times 3 to the n times negative 1 plus 2 to the n. Was it negative 1? No, it was 1 plus 2. It's positive 1 is the endpoint I care about. So 1 plus 2 to the n. This is the sum of 3 to the n over n times 3 to the n. This is the sum of 1 over n. That's the harmonic series. It diverges at x equals 1. It's the harmonic series, yeah. Cool. So our interval of convergence We almost knew it before. We knew it was -5 to 1. We just didn't know about the endpoints. We've now worked out that it converges at x equals -5. That gets a bracket. It doesn't converge at x equals 1. That gets a parenthesis. These are all the times the thing converges. It's an interval of radius 2. Cool. Very often... Oh wait, no, that's not in a radius 2. Damn it. We were centered at -2. The gap between here is the radius is 3. Radius of convergence is 3. My bad. Very often, the radius of convergence is going to be something to do with there's some number. These coefficients are basically exponential with a growth or decay factor of 1/3. That's going to tell you the radius is 1 over that. Very often you can sort of see what the radius is going to be beforehand. If it's a number, you probably see that number in the formula being raised to the n as part of the coefficients. That's power series and when they converge. A lot of problems we're going to do are of the form, hey, here's a power series, tell me when it converges. A second level question we're going to have is, can you tell me what this series converges to? Which feels unfair for that to be a question. We just did a bunch of problems about when I hand you a series, like when I handed you the sum of 1 over n squared plus 2, and we talked about limit comparison, and this is basically like a p-series. We made a big deal back then of we're going to figure out if it converges, but it's just way too hard to figure out what it converges to. It turns out the best way to figure out what it converges to is throw an x to the n on there. Thinking about functions is way easier than thinking about numbers because we get these tools to work with. So here's one of our new goals. Is to evaluate power series if we can. And we start with some baby power series that we can evaluate. For example, the sum of x to the n. I can do the sum of x to the n, because this is a geometric series. It's got growth, the thing you're multiplying by. Every step is you're multiplying by x. The thing I said about a geometric series is it converges, and converges absolutely, if that number has absolute value less than 1, and diverges otherwise. And the thing it converges to is first term over 1 minus r. Here our r value is x, and our first term is what do I get if I plug in n equals 0? It's 1 over 1 minus x. Fact. The sum from n equals 0 to infinity, x to the n, is 1 over 1 minus x, if x is between -1 and 1. This lets us evaluate a few other series. If you hand me sum of 2 to the n, x to the n. Well, since I can rewrite that as 2x to the n, I can tell you that this is going to converge to first term. This series weirdly starts at n equals 3, so the first term is 2x cubed over 1 minus our growth factor is here 2x. And it converges when 2x is between -1 and 1. That's when x is between -1/2 and 1/2. Notice I'm getting the interval and radius of convergence as a byproduct because I know when a geometric series converges. I get some facts for free without having to think about the ratio test or the root test when I'm using this trick. So right now, The only power series we can evaluate are the things that happen to be geometric. There's some good tricks we want to know, though. And it's basically figure out a way to turn a given power series into something that is geometric. The theorem we need to say is theorem. If f of x is the sum of n equals 0 to infinity a n x minus some value to the n converges on an interval, then the idea I want to do is take the derivative of both sides. F prime of x will be, what do I get when I take the derivative? N a n x minus x naught to the n minus 1. Here's a place where I might want to re-index it to not have, like having an n minus 1 makes it look not like a power series. So this is a good reason to re-index this thing. This will be from n equals 1 to infinity. Replace all these n minus 1s with n plus 1s. n plus 1, a n plus 1, x minus x naught to the n now. Then this series converges. And it converges to the right thing inside that interval, but not necessarily at the endpoints. By inside, I mean not at the endpoints. It has the same radius of convergence, but may behave differently at the endpoints. So the thing that we're saying here is you can take the derivative of a power series. The opposite direction also works. You can also integrate. So not just that you can take a derivative, but you can take a derivative term by term. The derivative of the left, you could guess, like derivatives work nicely under sums, but infinite sums are more suspicious than regular sums. It turns out you can take the derivative term by term. To take the derivative of the right-hand side, it's enough to take the derivative piece by piece. Except possibly at the endpoints. This thing will converge to the correct thing on the inside of the interval. The endpoints, it might not converge anymore. It might start converging. The endpoints might change. It's also not going to start converging outside the interval. The radius is staying the same. Right, I'm not going to try and justify this. Why this theorem is true. The other thing you can do is you can integrate term by term. If I have a function that converges on an interval, then the integral of this function, I guess there are infinitely many antiderivatives. Let's say, and if capital F of x is a function whose derivative is little f of x, then capital F of x equals, I don't know what the constant is. The constant of integration is going to turn out to be the first term of this series, which I don't know anymore. Plus, what do I get when I integrate this term by term? What's the integral of x minus x naught to the n? I add 1 to the exponent and divide by that n plus 1. Again, I have a power series that's written as a power series, but it looks goofy to have an n plus 1 there, so I am likely to want to re-index this to change that n plus 1. So when n is 0, 1, 2, that tells me n plus 1 is 1, 2, 3. Change this from 1 to infinity, and now replace all these n plus 1s with n minus 1s. A n minus 1 over n plus 1 minus 1 is n. X minus x naught to the n. And notice this thing is starting with the linear term. Our new series starts with the constant, with the linear term. It doesn't have a constant. The unknown constant of integration is filling in for that unknown constant term. And same deal. If this thing converges on an interval, then this thing equals this with the same radius of convergence, but possibly different behavior at the endpoints. So, let's try doing this. The idea is if you get a series that isn't geometric, maybe you can take the derivative of the terms, maybe you can integrate the terms, and end up with something that is geometric, and then you can evaluate that series, and once you know the answer, undo that derivative, undo that integral to figure out what the original series was. Let me show you what this looks like. Let's consider... Let's evaluate the sum from n equals, I shouldn't try and make one up on the fly, I want to pull out my notes. N equals 1 to infinity, minus 1 to the n over n, x to the n. So this thing's not geometric because there's an n here. What do I do to get rid of that n? If I took the derivative of this, taking the derivative of x to the n will stick an n out front, and that'll cancel with the n out there. I don't want that n out there, that's perfect. Then, f prime of x is the sum from n equals 1 to infinity of negative 1 to the n over n times n x to the n minus 1. In the statement of the theorem up there, I always re-indexed the series. We don't have to actually re-index the series. If I can evaluate, like, I don't care to use the formal statement of the theorem. The point is you can take the derivative that we just did. I guess the point is going to be we can untake the derivative and integrate back to say what f of x is the more useful thing. This is the sum from n equals 1 to infinity of negative 1 to the n, x to the n minus 1. I want to say this is geometric, but it looks goofy. This is a 1 over x times negative 1 to the n, x to the n. Like, this minus 1 is being a pain. I could re-index to get rid of the minus 1, but it's easier to rewrite this as x to the n times x to the minus 1. This is a constant I can pull out. It's undefined at 0. What's going on at x equals 0? Oh, the issue at 0 is that 0 to the 0 is undefined. Hey, here's a weird thing that happens all the time in these problems. You ask any mathematician what's 0 to the 0, they will always tell you it's undefined. Right? Because 0 to the something should be 0, but something to the 0 should be 1. So then you ask that mathematician, hey, how come you're allowed to plug in x equals 0 here? This function, when you try to plug in x equals 0, this is x to the 0 plus x to the 1 plus x to the 2 plus dot dot dot. When you try to plug in x equals 0, you're doing 0 to the 0. It's undefined. How come you said this thing equals this between -1 and 1? Actually, at 0, the thing on the left is undefined, because 0 to the 0 doesn't exist. Well, we'll just let 0 to the 0 be 1 here. Nobody ever deals with this. Like, the technical thing, when you write out these terms, they are technically x to the 0 plus x to the 1 plus x to the 2. But everyone crosses that out and changes it to a 1, which erases the fact that the thing was originally undefined at 0. This is not an important point that I'm saying about 0 to the 0 being undefined. This is me just pointing out that no one ever actually gets it right. So 0 to the 0 is undefined, except for us it's 1. There's like a huge... I kind of want to fill a book with the most annoying observations in the world about all the time smart people assume 0 to the 0 is actually 1. Anyway, yeah. That's manifesting itself in a weirdness here. This 1 over x is undefined at 0, and that's a form of the fact that there's a 0 to the 0 that's technically undefined, and it doesn't really matter. I'm going to factor that 1 over x out. I get -1 to the n, x to the n, that's -x to the n. And now it's geometric. And I know this equals 1 over x times first term. What's my first term? This thing starts at n equals 1. So the first term is -x to the 1 over 1 minus our factor, the thing that's being raised to the n, is -x. The 1 over x cancels with the x on top. Okay, this is the 0 to the 0 thing resolving itself. This equals -1 over 1 plus x, and it equals it whenever -x is between -1 and 1, which is when x is between -1 and 1. Okay, we know... So, we haven't found f of x. We found that f prime of x is -1 over 1 plus x, and it converges on -1 to 1. We know the interval of convergence and radius of convergence because we know those about geometric series. They converge when that growth rate or decay rate is between -1 and 1. When that factor r is between -1 and 1 is the only time a geometric series converges. The theorem we just said above tells us that our function also converges on -1 to 1, but possibly with different endpoints, or bracket -1 to 1, or -1 to 1 bracket, or -1 to 1 brackets on both. We don't know which of these it is, but the interval of convergence is the same except possibly for the endpoints. So that's good news. We don't have to manually think about that. We do have to figure out what our function is. F of x is a function whose derivative is this, so f of x is one of the antiderivatives of that. Can I integrate that? I sure can. It's negative natural log absolute value 1 plus x. The -1 stays out front, or is a constant. This is the baby substitution type thing. Plus a c. We don't know c. What do I know about my function? I know that my function's formula is sum n equals 1 to infinity. -1 to the n over n. X to the n. We said it converges. To evaluate c, I can plug 0 into the right-hand side. I guess I could plug in any number, but 0 is the one that doesn't generate a series. It's not always going to be 0. It's going to be whatever the series is centered at. There's always one point where the series is basically always 0, and that point is an easy point to plug in to solve for c. F of 0 is the sum from n equals 1 to infinity of -1 to the n over n, 0 to the n, which you want to say is always 0, except it's not at n equals 0, but there is no n equals 0 term, so okay, this thing is always 0. Remember, 0 to the 0 is defined to be 1 in this context. Equals negative natural log of absolute value 1 plus 0. So 0 equals 0 plus c. It turns out c equals 0. And there's our solution. we've evaluated that sum from n equals 1 to infinity minus 1 to the n over n x to the n does equal negative natural log absolute value 1 plus x on x between negative 1 and 1, and might equal it at negative 1 and 1 also. The theorem we said before says maybe it converges at negative 1 and 1, but it didn't promise that it would converge to the right thing at negative 1 and 1. It's a separate and somewhat more difficult theorem to, it turns out, yes, if it does converge, it will converge to the right thing. The left-hand side turns out it's going to be continuous if the limit if it's defined, it's continuous. And so it needs to equal, I guess it doesn't necessarily equal the formula, but it equals whatever the limit of this thing would be at the correct point. Depending on what the question is, sometimes I'll give a version of the question that just says find what function this converges to. Sometimes I will also say find when it converges to that. We've been keeping track of that this converges on negative 1 to 1. Let's go ahead and find the interval. Does it converge at x equals negative 1? At x equals 1? At x equals negative 1, this thing becomes the sum n equals 1 to infinity, negative 1 to the n, negative 1 to the n over n. That's a sum of 1 over n that diverges. That's the harmonic series. How about at x equals 1? At x equals 1, negative 1, n equals 1 to infinity, negative 1 to the n over n times 1 to the n. That's the sum of negative 1 to the n over n. That's the alternating harmonic series that converges. So we can conclude the sum from n equals 1 to infinity, negative 1 to the n over n x to the n equals negative natural log absolute value 1 plus x, and this holds on negative 1 to 1. Don't include negative 1, do include positive 1. Here's an example of us evaluating this series by taking a derivative and then integrating. We're integrating to undo the derivative. We took a derivative, we couldn't solve this version, but when we took a derivative we could, so we knew that this one was the integral of the derivative. Also, hey, note, you can plug numbers into this. At x equals 1, we've learned the sum of negative 1 to the n over n times 1 to the n is just 1, is negative natural log 1 plus 1. That's negative natural log 2. We just evaluated the harmonic series. Also, it's a less famous series, but we can plug in any number. We've learned that the sum from n equals 1 to infinity of negative 1 to the n, let's put in x equals a half. So I get n times 2 to the n on bottom. This is a series I could hand you and say, hey, what does this add up to? Without the x's there, this is really hard. When you throw the x's in, it becomes a thing you can start taking derivatives and junk with. What do you get when you get x's 2? You get, or what did I plug in? I plugged in a half, so I get negative natural log 3 halves. Maybe I can feel fancy and write that negative natural log 3 plus natural log 2. Is that cool? I don't know. Right. We can sometimes evaluate power series, and those give us series that we've evaluated. Like, evaluating a power series means evaluating infinitely many series, because you've done it for infinitely many x values. Let's try a slightly trickier version. I'm gonna not make the mistake last time and write a version that I can't solve. Oh, actually. Let's shift gears a little bit. So this is about, given a power series, can you find the function that it is? We're also going to ask the questions the other way around. Given a function, can you find a power series for it? Centered at some x value. I'm usually going to say centered at 0 in this context. Although maybe there's a couple in the homework where we didn't. Let's start with the basic ones we know. 1 over 1 minus x. We know that that is the sum of x to the n. Can we work out some more functions from that? Well, I can sort of add some variations on it. If you hand me 1 minus 3x, that's going to be the sum of 3x to the n. This is true for x between -1 and 1. This is true for 3x between -1 and 1, so that'll be from x between -1/3 and 1/3. I get that type of thing for free. If you hand me 1 over 2 plus x, okay, now you've messed it up in two ways. That number is wrong. If I factor a 2 out of the bottom, I can write that as 1 plus half x. I can factor out that 1/2 and write it as 1 over 1 minus -1/2 x. The key thing is I know what to do with 1 over 1 minus blah. So if you hand me anything else that looks kind of like that, can I figure out the way to force it to look like 1 over 1 minus something? And here, factoring out a 2 and adding in a double negative gives me a way to do that. This thing is going to equal 1/2 the sum of that to the n minus 1/2 x to the n. I guess if I'm being precise, I should say these were all from 0 to infinity. And this converges if -1/2 x is between -1 and 1. So that's going to be when x is between -2 and 2. This doesn't quite look like a power series because there's this constant out front, but I can make it look more power series-y if you make me by pulling that x to the n out. What is on the x to the n? -1 to the n and 1/2 to the n, and with one more, n plus 1. You can throw in goofier powers of x. If you hand me 1 over 1 minus x cubed, well, that's going to be the sum of x cubed to the n. This is a thing that doesn't necessarily look like a power series. Like, the definition of a power series was just powers of n. This turns out to be the easiest way to write a certain type of power series, though. Let me say when this converges. When x cubed is between -1 and 1. When is that? That's when x is between -1 and 1. What does this series look like? It looks like 1 plus when n is 1, you get x cubed. When n is 2, you get x to the 6. When n is 3, you get x to the 9. I can believe that this is a power series that's just missing some of the terms. That just means you've got a coefficient of 0 on those terms. I think if you're being fully precise, if you want to write this as a power series, the thing you need to do is you need to say let an be 1 if n is divisible by 3. Or it's 0 if n is not divisible by 3. Then 1 over 1 minus x cubed is the sum of an x to the n. Like, you need to specifically come up with a sequence that equals 0 for the missing terms. This is the technically correct way to write this as a power series. But nobody ever really wants to write it like this. You're totally allowed to just say x to the 3n as a shorter, easier way of saying we're only going to be using this exponents that are multiples of 3, right? You don't need to come up with a sequence that equals 0 at all the other times. You might even be able to come up with a formula, like using some sin n pi something something. Like, there are goofy tricks to generate a series that equals 1 for divisible multiples of 3 and 0 when it's not. But using those tricks doesn't make your series easier to understand or easier to read, and it doesn't make you smarter for having come up with it. So we don't usually... Doing that makes it harder, not easier. If someone hands you that, maybe it's good to figure that out and then rewrite it in the other way and then evaluate the series. So... we also want to be able to find power series for other functions. Let's find a power series expansion. For tangent inverse x. Centered at 0. By default, we're going to do these centered by 0 unless someone tells us to do it otherwise. I guess I should do one that's not centered at 0. What do I know about tangent inverse x? The main thing I know about it is its derivative. Like, I don't want to have to do some trig stuff. Nothing we've seen about power series is good for trig stuff. What's the derivative of this function? The derivative of tangent inverse is 1 over 1 plus x squared. Hey, that's the type of thing I'm good at. Can I make this look like the kind of thing I can do a power series of? Yeah, I can make that as 1 over... I want it to be 1 over 1 minus something. This thing is 1 over 1 minus negative x squared. Aha, that's going to be the sum of negative x squared to the n, from n equals 0 to infinity. And it converges when negative x squared is between negative 1 and 1. Well, this is positive. Being bigger than negative 1 is irrelevant. Wait, no, it's negative, so being less than 1 is irrelevant. You get x squared less than 1. That's going to be x is between negative 1 and 1. So I'm able to come up with a power series expansion for f prime of x. I'd probably like to clean that up a little bit. That's going to be negative 1 to the n, x to the 2n, is the derivative of that tangent inverse. One of the facts we said is if a power series converges, you can integrate it term by term. So f of x is some constant plus... you put the constant first for a series, because you don't want it to look like the plus c is inside the series. Like, what I mean is if I put a plus c here, it tends to look like that there's parentheses around that, or something. When you write a big sigma, you kind of want everything after the sigma to be inside the sigma, because we don't put those in parentheses usually. What do I get? Integrating this term by term, x to a power is going to be add 1 to that exponent, divide by that new exponent. Again, this is the type of thing where I might feel the instinct to reorganize this, to re-index. This is the standard notation for saying we only are using odd terms. 2n plus 1, the sequence 2n plus 1 from 0 to infinity is 1, 3, 5, 7, 9. This is a situation where my series has only odd terms, and using x to a power of 2n plus 1 is the easy way of saying all the even terms have coefficients of 0. Those aren't there. I need to figure out my c. I can figure out f of 0 is tangent inverse of 0 is 0. So c, the constant term, is 0. Or, I guess we haven't noted that c is always the constant term. C plus, when I plug in 0, is c plus 0. There is no... I should be checking for myself that I've done a thing that could be a mistake. Saying 0 to any power is always 0 is not true, because 0 to the 0 is 1 in this context. But 2n plus 1 is only odd numbers. We're not using 0 to the 0. So, yeah, is f of 0 is 0. C is 0. I think I have not explained that correctly, but C turns out to be 0. Cool. That's power series. There's 2 versions of the problem. I guess 3 versions of the problem that we've seen today. There's, I hand you a power series and you tell me the radius and interval of convergence. There's, I hand you a power series and you figure out what the power series is. You do that by integrating or differentiating or maybe factoring some junk out until it turns into something exponential. You evaluate that series and then backtrack to figure out, well, what was the thing you gave me then? If I just worked out the derivative is this function, that means my thing should have been the integral of that. Figure out the constant. Or if I hand you a function, you tell me a power series expansion of it. Oh, I should do one more example where it's not centered at 0. Let's do our basic one, but centered at a weird point. Find a power series expansion. Of 1 over 1 minus x, centered at x equals 10. If I'm centered at x equals 10, then I'm thinking about a sum of x minus 10 to the powers. I'm thinking I want a 1 over 1 minus an x minus 10. This is all happening in my head. Can I make this look like an x minus 10? I guess I can... A thing I can always do is just change x into x minus 10 plus 10. And now figure out what to do to get this out of the way. That turns into 1 over 1 minus x minus 10 outside of the parentheses minus 10. 1 minus 10 is negative 9, so I'm rewriting this as 1 over negative 9 minus x minus 10. Okay. Okay, and we did one like this, where we didn't like the fact that we had a constant out there. The way we dealt with the constant that was out there was we factored it out. Maybe a nice way of doing that is to multiply the top and bottom by 1/9, or negative 1/9. If I multiply the top and bottom by negative 1/9, I get negative 1/9 on top, that's a constant, I can pull it out. On bottom, I get 1 minus, so I put a negative 1/9 in here. It's tempting to get rid of this minus, but I want that minus there. I'm just going to put the negative inside the parentheses. X minus 10 over negative 1/9. So I've got, this is negative 1/9 times 1 over 1 minus. That 1 over 1 minus is the magic thing I'm looking for. X minus 10 over negative 1/9. Because I have memorized that 1 over 1 minus blah is the sum of blah to the n. Like, that's the thing you really want access to on the tip of your tongue. And it equals that if blah is between negative 1 and 1. I'm probably going to actually have to solve it this time. Multiply all 3 sides by negative 1/9, and I get negative 1/9 and 1/9. X minus 10 is between negative 1/9 and a 9th. X is between 10 and a 9th is 91 over 9. 10 minus a 9th is 89 over 9. We got this weird interval of convergence. And I could probably stand to clean that up a little bit. This is the sum from n equals 0 to infinity of negative 1/9 over negative 1/9 to the n, x minus 10 to the n. Okay, there's a negative 1 to the n there. That deals with the negative inside here. This is 9 to the n over negative 9. That seems pretty clean. I wrote to the 9. That should have been to the n. Here's a power series expansion for the same regular function centered at x equals 10 this time. So this is how to make that happen if they tell me to center it at a weird thing. It's usually just a matter of change this to an x minus 10 by fixing the constant, and then fix the other constant by pulling out a factor or putting in a factor, or however you want to think about that goofy step. Okay, let's talk about homework. This stuff is by and large way easier than the stuff we've been doing. I save it for the end of exam 2 because you don't want to put the hard stuff at the end. We skip the Taylor polynomial stuff first. I saved that for after this thing. But the problems you can do are now 120 through 132. Oh no. Dang it. 120 through 124. The plan for the rest of the week. Today's Wednesday, right? Yeah, okay, tomorrow I'm going to cover the last topic. Taylor polynomials and series. Friday I'll do a recap. I guess I'll probably go over the practice exam. And we're probably ready to do the exam on Monday. I'll let you know for sure by Friday. Tomorrow and Friday, I am still open to going over student work on the other stuff. If you email me some problems you did, I am happy to talk about sentence construction and all the no fun details. So far, I did things that were basically correct that would lose at most a point or two for weird sentence phrasing, but that were using all the right techniques. I think it would be instructive to do some where someone used the divergence tests when they weren't allowed to. Like, it would be helpful if we talked about some problems that went wrong. If you have a problem you think you did wrong, feel free to send that to me. If you don't want me to talk about your problem in class, that's fine. I can get back to you privately. But I really want to be doing this in front of you guys as much as we can to talk about, like, what are some things to look for that are going wrong. And if you don't feel ready for the exam Monday, the way to slow me down so I don't get through this stuff is to show me a bunch of problems you want to see me do. I'm open to doing homework problems or reviewing your problems or whatever. But we need to... Yeah. I think I said what I'm saying. I'm exhausted. This was a rough one today. I'll see you guys tomorrow. End stream.